Let's consider here an example of how we apply the principle of conservation of energy to problems that include elastic springs. We'll consider a problem of elastic spring without friction. A 300-gram block is attached to a spring with a spring constant equal to 10 newtons per meter. It is pulled 10 centimeters away from its equilibrium and is released to slide along a smooth surface. The question will be, what is the maximum speed of the block and where along its motion does it happen? So let's start with the second question first. But first let's mark our equilibrium position here with x equals 0, and this will be the position x equal to 0.1 meters. This is our starting position. A quick review, a reminder here, since this is our first example about elastic spring and elastic potential energy. The elastic potential energy formula is 1/2 kx squared, where k is the spring constant, and the problem here gave it to us as 10 newtons per meter. So now let's look at the diagram here and see if we can figure out where along the motion of that block we will actually see maximum speed. Maximum speed will correspond to maximum kinetic energy, and given that the kinetic energy added to the potential energy will always have to add up to a certain amount of mechanical energy, we can see that the maximum kinetic energy will be when we have minimum potential, in other words, when we have zero potential energy. Zero potential energy corresponds to zero displacement, because the formula is 1/2 kx squared, and so we see that the location where we're going to see the block moving at maximum speed will be when it's passing through the equilibrium position for the spring. You can look at that from a different angle. If you think about the elastic force of a spring, this is the location where something changes drastically in the behavior of the spring. Up to that location, the spring has been pulling the block and making it speed up towards its equilibrium, but once it passes the equilibrium, the spring begins to push in the opposite direction to try to stop the block. So with that, we can actually go and look at the total mechanical energy. First, at the location where x is 10 centimeters or 0.1 meters, kinetic plus potential will give us 1/2 mv squared plus 1/2 kx squared. Of course, starting from rest, or in other words, if we release the block at that location, that implies that we start with a zero speed here. So the total mechanical energy at this location will be simply equal to whatever we have in the form of potential, elastic potential energy. Now let's go and see what happens during that at the location where the block passes its equilibrium. The total mechanical energy at x equals 0, being kinetic plus potential, is 1/2 mv squared plus 1/2 kx squared for that location. For that location, of course, x is 0, so we see that the total mechanical energy at that location will be equal to whatever we have in the form of kinetic energy, 1/2 mv squared. The principle of conservation of energy will set up that the two energies have to be equal. In other words, E at x equal to 0.1 has to be equal to the energy E at x equals 0. In other words, 1/2 kx squared will have to be equal to 1/2 mv squared. I'll cancel 1/2 here, and we'll see that the square of the speed with which the block passes through its equilibrium position will be equal to k, the spring constant, over the mass of the block multiplied by the square of the original position x. Numerically, that will be 10 over 0.3. I have switched here the mass of the block from grams to kilograms, multiplied by x squared, which is 0.1 squared. Or V will be 0.577 meters per second.